So my name is Ingo Stelzer from Curare Europe, Advanced Interlayer Solutions. So I'm the chairperson for this session. So let me introduce our first speaker. It's Olga Panina from Corning Glass. So Olga is based in the Helsinki research facilities and working on tests and research projects for Windshield projects and other projects, I guess, too. And so her topic will be the simulation of windshield performance across diverse laminate thicknesses, glass compositions, and designs. So please welcome Olga. And Olga, the stage is yours.
Yeah, thank you for introduction. Hello, everyone. My name is Olga Panina, and today I will present this work on behalf of our team. So this work was done with my colleagues Nikolai Antipin and Sergei Shubin from Corning. So let's start. I would start with outline. First of all, this presentation will be about simulation of the pedestrian protection test, or in other words, head impact test. And I will start with the background, why we are looking at this problem. When I will describe our modeling approach and show validation of our model. Then we'll show how we implement our model for different asymmetric windshield constructions, and we'll complete my presentation with the summary. So the background, some of you might be aware of this test, pedestrian protection test, which is actually an industry standard, and the goal of this test is to make sure that in the event of the collision between a vehicle and pedestrian will not receive high injury, and basically this test is performed in a way that the head form is impacted the windshield and the deceleration is measured into the head form. And based on the deceleration curve, so-called head injury criterion is calculated, and this head injury criterion should be within a specific threshold to not cause the high injury for the pedestrian. So this is the main idea of this test. What about the windshields? The kind of conventional windshield in the Europe is a 2.1 outer ply, 1.6 inner ply soda lime with the 0.76 PVB interlayer. And what do we know about this construction? The performance of this construction is pretty well studied, and there are a lot of established simulation approaches for this kind of test. Also, this construction with us for a pretty long time. It has not changed since 1960s. And here we can ask a question. Does it really address needs of the modern vehicles? Let's take a closer look. First of all, probably note, because there are some pressing needs of innovative windshield solutions. Now, all we see that advanced support systems for drivers, such as heads-up displays, present in the cars, which makes a really high replacement cost in case of the windshield breakage. So that's why there is a really need in the enhanced durability, so windshield can serve longer. Another thing is optical performance. Again, once we have all of these display systems, optical performance is really important. And here there is an example of the heads-up display image, how it appears with the thick and thin glass. And here you can see a ghost image in the thick glass, and in the case of the thin glass, it is a much better quality. So that's why there is a need in thin and excellent optics windshield. And the last point is, of course, CO2 reduction and fuel economy. We all want vehicles to be lighter, to spend less CO2, and to spend less money on the fuel. So that's why lightweight is also a very important factor. But how it all be addressed? Actually, we have Corning Fusion 5 glass and Corning Gorilla glass, which could address these industry needs. So Corning Fusion 5, how you can imagine from its name, it's a borosilicate glass made by fusion process, and Corning Gorilla, it is a chemically toughened glass. So let's take a closer look how it addresses the needs listed on the previous slide. So we were talking about enhanced durability, and here borosilicate glass as an outer ply provides superior sharp impact resistance in case of the sharp impacts like stones impacting the windshields. And here you can see an example of the Vickers dart drop test. On the left-hand side, you can see the clear failure of the soda lime construction from the 600 millimeters, while on the right-hand side, you can see not such a large crack for the Fusion 5 Gorilla Glass construction from the 3,000 millimeters drop height. Also, due to the borosilicate properties, it has up to 5 times better scratch performance, and due to the CT, also provides better thermal shock resistance, which is also important for windshields. You can imagine if you have like small damage on your windshield and you decided like to wash your car by the like cold water in the hot summer, it could easily propagate. So thermal shock resistance is also important factor for windshield durability. So the next point is the thin and excellent optics, and here we can easily use really thin inner ply. For example, replace 1.6 conventional soda lime by 0.7 Gorilla Glass, which will like 2 times lower thickness. Also about the optics, due to the fusion process of the glass, we have really superior optical properties. And here you can see the comparison of the fusion glass with the flawed soda lime glass. And due to the better scratch performance, we will also have much lower optics decay. Talking about the lightweight, I have already mentioned the thickness. So obviously, due to the lower glass thickness, we will have significant weight reduction. But also due to the lower density of the Fusion 5, it also contributes to the weight reduction. So you can see that these glasses address industry needs, but if you remember, we started from the head impact test, so here is a reasonable question. How does this construction perform in the pedestrian protection test, which is an industry standard? To do this research, we developed a model to simulate the performance of such type of glasses. And here is a model overview. Model consists of the windshield itself, of the 2 glass layers simulated by the shell elements with the PVB interlayer simulated by the solid elements. Also, we have a head form and in the head impact test, glass breaks, and we have to take it into account into the model. To do so, we need to define a very robust failure criterion for different types of glasses. And here we were using a nonlocal failure criterion, which consists of the 2 parts, 2 main parameters. Critical stress, tensile stress and compressive stress, and 2 parameters for the energy parameters, critical radius and critical energy. What does it mean? Basically, critical energy is internal energy measured into the circle defined by the critical radius. And here, how this parameter is formulated to like breakage to be happen, 2 parts of the parameter should be satisfied at the same time, both stress criterion and energy criterion. And this criterion is actually implemented into the LS Dyno. So here is a validation of our model, and I will show validation for different points. We will start with the different windshield shapes. So and we will be validating our model based on the head deceleration. So you can see these curves. This is the deceleration measured into the head during the impact, and the test outcome itself, it is a head injury criterion calculated based on the deceleration curve by the standard formula. So you can see into the comparison the blue modeling result and the red experimental data. We can see pretty nice correlation as curve shapes and absolute values of the head injury criterion as well. So we see that accuracy of the model is independent on the windshield shape. Another validation point is a glass composition. How does this model works for different glass compositions? Here is an example for the 2.1 soda lime outer ply with the inner 0.7 Gorilla Glass inner ply. And again, we see nice agreement between modeling and experimental in both curve shape and head injury values. And on the bottom of the slide, a comparison of the two similar constructions with the similar thicknesses, but in the right-hand side case, it is a 3 mm Fusion 5 outer ply, and on the left-hand side case, it's a 3 mm soda lime outer ply. And for all of these cases, model provides robust predictions. And the last point, it is a head form type. So in the test specification, there are two head types, child head and adult head. And again, we have validated it with the experimental data and demonstrated that model works accurately for all of these parameters. Okay. So now, once we validated our model, we can explore different combinations of the glass compositions and thicknesses. And let's take a look how it looks like. So as a baseline, we picked the conventional 2.1.1.6 soda lime construction to compare with, and picked several constructions with the novel glass compositions and with the different thickness variations. So you can see a few constructions which total thickness is slightly higher than the conventional one, and two constructions which could really provide like lightweight solutions. So it could be very different range, but this is done just for the comparison to show the different range of the constructions and its performance. And here are the results. You can see the chart and numbers presented. These numbers show the head injury values, and colors mean the performance criteria. So here you can see the scale. This is the Euro NCAP performance criteria, and basically green zone means the best score, and the darker color, the worse. And you can see that conventional soda lime windshield has 230 head injury criterion, and all the considered constructions have pretty similar results, meaning that all the constructions may successfully pass this test with the highest score, and that results of novel constructions and asymmetric constructions are similar to conventional windshields, which means that there is a pretty little effect on the performance of pedestrian protection test from the novel constructions. So to sum up, we discussed the background and demonstrated that Corning Fusion 5 and Corning Gorilla Glass in the windshields could address industry needs, namely durability, providing the superior sharp impact, scratch and thermal shock resistance. They are thin and have excellent optics. Also provide lightweight. And by our modeling approach, we demonstrated that there is almost no effect of these constructions on the performance in the pedestrian protection test. So in the conclusion, I would like to thank you for your attention. And if you are interested in collaboration, let's get in touch. Thank you.